गुड इवनिंग एंड वेरी वार्म वेलकम टू द ब्लैक होल। आज की गुफ्तगू का उन्वान है स्पर्नर लेमा, केक कटिंग, रेंटल हार्मनी एंड द ब्रावर फिक्स्ड पॉइंट थ्योरम। मुझे इस मौजू के बारे में कुछ भी इल्म नहीं है, लेकिन मुझे ये पता है कि डॉक्टर सरमद अब्बासी जब लेक्चर देते हैं तो वो सिर्फ लेक्चर नहीं होता, बल्कि एक आप यूँ कहें कि वो बिल्कुल एक स्टोरी टेलिंग सेशन होता है जिसमें आपको बहुत दिलचस्पी महसूस होगी। और ये कि मैथमेटिक्स उनकी 10th ग्रेड से ज़्यादा रिक्वायर्ड नहीं होती जो उनको सुन रहे होते हैं। सो आई होप कि सेशन के अख्ताम तक आपको इस मौजू के बारे में और मुझे भी काफ़ी हद तक आगाही हो जाएगी। डॉक्टर सरमद अब्बासी लाहौर से तशरीफ़ लाए हैं, इसके लिए हम उनके बेहद शुक्रगुज़ार हैं। आप उनको जानते हैं, ही इज़ एन एजुकेटर, थ्योरेटिकल मैथमेटिशियन, और इसके अलावा आप एक यूट्यूब चैनल रन करते हैं नेम्ड एज मैथ कैट, which aims to promote mathematics and theoretical computer science. So let's welcome Sarmad Abbasi. Thank you.
Thank you. Thank you. Okay, so we are going to, so let me start with a practical problem and then we will go to a little technical thing. So let's say that there are students who have decided to rent a house. Okay, and the house has 3 rooms. Okay, one red, one of them is blue, and the other one, let's say, is yellow. Okay, and you know, these rooms are different. They are different in sizes. They are also different from other respects. One of them may have a window, the other one may have something else. Right? So they've decided to rent this house, and now what they want to do is they want to decide who is going to get which room and what is the share of the rent each person is going to pay. Right? So simultaneously they want to decide that, and they want to do that in such a way so that so they don't get envious of the other person. Right? So that's a very practical problem we can think about. And the way we will solve this problem is using something called the Sperner Lemma. Okay, which is a very beautiful combinatorial result. And then once we have proved this, then we'll apply it to the roommate problem, the rental harmony, and also other problems. Okay, so let's look at the statement of the Sperner Lemma. And here's the simple statement. What you have is a triangle, okay? And on this edge, you are not allowed to put yellow color, okay? And you have 3 colors. And you have a large triangle which you have cut up into smaller triangles. So this thing is called a triangulation of the large triangle, and you have little triangles. Each shape in here is a triangle. And what you're going to do is you're going to color the vertices, and the rules are no yellow on this side, no blue on this side, right, and no red on this side. Okay? All right? So that forces you, since there's no yellow and no blue on this side, you have to put a red here. And since there is no red and no yellow on this side, you have to put a blue here. For the same reason, you have to put a yellow there. So the idea is you pick 3 corners and you put 3 colors there. And on that edge, the opposing side's corner's color cannot appear. Right? Those are the rules of coloring this triangulation. What about the inside triangles? There are no restrictions. You can put any color that you want on them. All right? And so now what does the Sperner Lemma say? So the Sperner Lemma says that no matter how you do that, respecting these rules, and no matter how big a triangulation you have, how fine a triangulation you have, you're always guaranteed that there is a multi-colored triangle. Okay? All right, so for example, in this picture, multicolored little triangle. Okay, a little triangle on which all three colors appear. Can you find one in this figure?
Yes.
Yes?
Next to the cake.
Next to the cake, this one. Yeah, all three colors appear. Right, and it says no matter how you color it, no matter how big this thing is, you will always find a little triangle in which all three colors appear.
The top triangle is all red.
Yeah, that's a monochromatic one. Okay? So Sperner Lemma is not looking for a monochromatic triangle. It's looking for a colorful triangle in which all three colors.
Sir, your lecture started at 6 p.m.?
No,
6:30?
no, it just started.
Just started, okay.
Yeah, you can catch up. Yeah. Okay?
I was worried, okay.
All right, so let's see the statement of the Sperner Lemma. We have a large triangle, we triangulate it into little triangles. And now the rules are that you put three colors on the endpoints. And on this edge, the opposing color cannot appear. So you can't put yellow. On this edge, the top color can't appear, so you can't put red. On this edge, the opposing color cannot appear, so you get no blue. That is the rule. The inside triangles you can color any way you want, no restriction. And the conclusion of the Sperner Lemma is once you do that, there will always be a little triangle which has all the colors. Okay, all right. So that's the Sperner Lemma. Now let's start proving it. Okay, and the proof is really, really beautiful. Okay, so what I'm going to do is I'm going to pick two colors. So in this case, I'm going to pick blue. All right, and then I'm going to pick yellow. All right, and every time I see an edge which has these two colors, I will create a door here. Okay, right? So think of all these little triangles as rooms. Okay, and every time we have a blue vertex connected to a yellow vertex, I will create a door. Okay, so let's do that. So in this case, I have a door here. I have a door here. I have a door here. Door here. I have a door here. A door here. A door here. A door here. This is a door. Right? I think this is a door. All right. Where else do I have a door? This is a door. This is a door. That's a door. And this is a door.
The bottom one seems to be a mistake.
Yeah, this is a mistake, definitely. And thankfully you caught that mistake. Yeah, that's not a door. Is there another mistake?
There should be a door on top. Blue and red gets connected.
Where?
Blue and red are connected.
No, we put a door only when blue and yellow are connected. We just pick the two colors, okay? All right. So now here's an observation that when you look at a little triangle, you ask yourself how many doors can it have? Okay? So it can have 0 doors. You know, here's a triangle with 0 doors. You know, if blue or yellow doesn't appear in it, it'll have 0 doors. It can have 1 door. Okay, so let's say it has a blue and a yellow appearing here. So it has 1 door. Can it have 2 doors? Right? Yes, if you have a blue here, then it will have a second door. If you have a yellow here, then you have a second door. But it cannot have 3 doors. It cannot have 3 doors, you know, because 2 is the best you can do. And which are the rooms which have only 1 door?
Multicolored.
Yeah, the multicolored. Okay? All right, so what are we looking for? We're looking for rooms that have one door. Okay? So that's what we're looking for. Now let's make an observation. On this edge, there are no doors. Because remember, no blue. Blue is missing. Can't have a door there. On this edge, there are no doors because yellow is missing. On this edge, obviously, we have doors. The question is how many? Okay. And my claim is that on this edge, I can't tell you how many doors will there be, but I can tell you their parity. There will be always an odd number of doors. Okay? And why is that? Because remember, every time you see a door here, you switch the color. All right? And you're starting from blue, you're ending at yellow. So you must switch an odd number of times. Okay? All right? It's just like a light bulb, right? So think of this as off and on. It stays on, off, and then on. So if you started with off and you flip the switch over and over again and end up with an on, you must have switched it an odd number of times.
If we had like blue, yellow, then wouldn't we have 4 doors?
Blue, yellow, blue, yellow, blue.
Blue, yellow, blue.
Yeah, but then you ended at blue.
Alternating.
Yeah, but you ended at blue.
So
You have to.
अच्छा हाँ उस side पे blue नहीं होना चाहिए.
Yeah. So you have to start from a blue and then you have to end at a yellow. So you have to have an odd number of doors. Okay. All right. So in particular, there should be at least one door there. You have to switch at least once.
Yes.
All right. But an odd number of doors. Okay. All right. So now let's go hunting for our room that we are looking for. Okay. So what I'm going to do is I'll enter from the bottom and I go into a room. If it has 2 doors, I just come out of the second door. Okay? This one has 2 doors, I come out of the second door. This one has 2 doors, I keep doing that. Well, what will happen? 2 things can happen. One is that I enter, I take a tour, and I come out from some other door. All right? In that case, my hunt was unsuccessful. I wasn't able to find it. So what would I do in that case? I will discard these 2 doors, okay, and go for my hunt again. Find another door and enter it. Okay. So every time I'm unsuccessful, how many doors do I discard? 2. But there are odd number of doors. So there must be one door which is successful, which doesn't come back.
Okay.
All right? And so in this case, you can see that you go from this door, and you go and you get stuck, and you're happy. You've found your... Okay? Yeah. Okay. All right? Yeah. So let me just do the argument again. It's so beautiful, very quickly. First observation, you can't come out from this side. You're sealed here, no doors. You can't come out from this side, you're sealed here. So the only side you can enter and come out from is the bottom side, number 1. Number 2, on the bottom side there are odd number of doors because you start from a blue and you end at yellow. So you must switch an odd number of times. Okay. And now you go hunting for your room that you want to get stuck in. If you're unsuccessful, that gets rid of 2 doors, right? But since the total number of doors is odd, there must be one which leads you to a door that is stuck. Okay, all right, so that's the Sperner lemma. Now, let me ask you, to prove something slightly more. The number of multicolored triangles is not just 1, it must be an odd number also. Okay? And what will be the argument for that? Okay? All right, so Sperner Lemma says that there must be a multicolored
Yeah, because
triangle, right? I'm saying there must be an odd number of multicolored triangles, which is a more general statement, because 0 is not odd.
because the parity of the doors on the bottom. यार तुम जो है ना मेरी सारा बीच में ठोक देते हो. Because the parity of the bottom edge is odd, so that's why doors will get eliminated in pairs, and you can, so if you start with, for example, you always have, you start with an odd number, and elimination takes away pairs. So if you start with an odd number, you take away twos and twos and twos, you always end up with an odd number. So 5 minus 2 3 minus 2 1, or you start with any 7 minus 2 5 3 1 and so on.
Yeah.
So you will always end up with an odd number of like these.
Yeah.
multicolor.
So what you can do is the tours that you took, you classify them into successful or unsuccessful. The unsuccessful ones account for even number of doors.
Yes.
And the successful ones account for the remaining, which is an odd number of doors. And so therefore the number of odd. But this argument is not complete. Okay? And the reason it's not complete is, let me change this coloring a little bit. Okay, how do I do that? Okay, so maybe I do that. Okay, so here's this thing, and you are discarding doors in pairs like this, and this is your successful tour, this is another, and there's a third one. Okay, but can there be actually other multicolored triangles that are not reachable from there? Okay, so yes, the ones that you can reach, they are odd. Okay, 1, 2, 3. But can there be others which are just not reachable from downstairs? Okay, and that's, you have to argue that they are even also.
These can exist isolated.
Yeah. So let me sort of make. So let's say this is red, yellow, and blue, and let's say this is red. Okay. So now there is a door here. Okay, and this is sealed off from all sides. You can't reach it. Okay, all right. So the argument is not complete. Our successful tours are going to be odd. That's true. But what about these other multicolored doors that we cannot reach? Okay, so this is one line argument, and then we'll be done.
Are they going to be even?
They are going to come in pairs. They have to come in pairs because here's a room which you can't reach.
Exactly.
Follow the door.
Yes.
All right? Either you get stuck again, or there are two doors and you keep going. All right? So it gets paired with where you get stuck again.
So what are we trying to prove right now? That
the total number of multicolored triangles are odd. Okay.
including these isolated ones.
Yeah.
Yes, because odd plus even is always odd number. That's
Yeah.
why they must, total number must also be odd.
Yeah. So that's the argument. Okay. All right. So this is Sperner Lemma in 2 dimensions. All right. So before going further, let's do Sperner's lemma in 1 dimension. Okay. In 1 dimension, Sperner Lemma just says that you have 2 colors. One is blue and one is yellow. And you have taken this segment and cut it up into small pieces, and you have no rules on the internal vertices. You can color them red or blue. All right? Okay. Let's say you color these 2 blue and the other yellow. Sorry, yellow or blue. And in 1 dimension, it says that there must be an odd number of multicolored edges. Okay? And in 2 dimensions, you play the same game, and it says there must be an odd number of multicolored triangles. Now you can play this game in 3 dimensions also. Okay? So in 3 dimensions, you take a simplex, right, which is a tetrahedron, all right, and you cut it up into smaller tetrahedron. Use your imagination. My drawings in 3 dimensions are terrible. They're bad enough in 2 dimensions. Okay, and now you say that on this, now you have 4 colors. So you have, let's say, blue, yellow, okay, red, and orange. I didn't bring green, so it has to be orange. So you have 4 colors, and now once again the restriction is that on this face no blue, okay, on this face no red, on this face no orange, and on this face no yellow. Okay, that on the point, on the opposing face of the point, that's not allowed. And then inside you can color with any colors you want. And the conclusion is now that odd number of tetrahedron, multicolored, where all 4 colors appear. Okay, and the proof, I want to do this because the proof is not, that's where all the difficulty is. The proof is not difficult here, all right? Because you do exactly the same proof. But first you say, let's look at the bottom surface. It's exactly the same thing as that problem, all right? So that means that there must be an odd number of multicolored triangles at the bottom surface. So let me draw one.
You can say that for all 4 sides. Right?
Yeah, but here we just fix 2 or 3 colors and say it for that one. Okay, so there must be an odd number of multicolored triangles like this. Now what you do is you take a tetrahedron, okay, little tetrahedron, and you put a door in it if these 3 colors appear there. Okay, so now you think of this tetrahedron as a 3-dimensional room. Okay, and if these 3 colors appear there, on that face you put a door. Okay, so yellow, red, and blue appear. So there will be a little door here. Okay, you make a door here, punch a hole. Question is, how many doors can a little tetrahedron have? There are 4 potential faces. Can they all be, Okay, so let's say it has 1, which is the bottom one. What are the choices you have here?
Then orange.
If you put an orange, you don't get any more doors. Right? If you put a yellow, then you just get 1 extra door. One is the one here, and the other would be the one when you hide here and that. Okay?
So you can only get 1 or 2.
You can get only 1 or 2 doors. And what are you looking for?
For 1 door.
1 door, the multicolored one. Right? Right? And now the argument is the same. You have odd numbers of doors at the bottom by induction from here, all right? And you're looking for a room in which you get stuck. So just take a tour. If you come back, you discard. Okay, it's exactly the same argument. Nothing changed. Okay, it's exactly the same argument.
And also,
right?
The isolated ones come in pairs.
Isolated ones come in pairs. You argue that, and that's why actually you need this strengthening of the Sperner Lemma. That you don't want to say there exists a multicolored door. You want to say that there are odd number of them, because you use that in the inductive argument, right? You know, I didn't use only the fact that there's one door here. I needed odd number of doors for that to continue. Okay, all right. So, well, what does this have to do with cake cutting and what do you call it? Rental harmony.
Excuse me. I have a question. So, okay, we are having Sperner's lemma. We can see in a line it works. We can see in a plane
It works.
it works. Then why don't we use induction instead of going to these simplex thing in 3 dimension? We just use induction and we can prove it for n. Would it be
No, we did use induction. Induction हमने use की ना देखो 3 में जाने के लिए right ये मेरा simplex था ना उफ sorry let me yeah ये मेरा
नीचे ले आना ऊपर से
I think
पहले आपने बताया था हाँ ऊपर से टॉप वर्टेक्स से नीचे
ओके सो इसमें हमने पहले ये आर्ग्यू किया कि ये जो बॉटम इसकी साइड थी दैट इज जस्ट द 2-dimensional केस ओके सो बाय इंडक्शन देयर मस्ट बी एन ऑड नंबर ऑफ मल्टी कलर triangles there. Okay, and now we said that if those colors appear, we make a door there. Okay?
Yes. So
Or-
my question is this. So you have shown it on a line that this point is blue and this point is yellow, and then you have shown the argument of Sperner's lemma.
Yeah. Yeah.
Why don't we take that one as base case and this one, which is drawn beautifully over here in 2D in front of us, this one, we use it for the sake of induction for k plus 1. And then we don't need to draw this particular pyramid.
So, okay. See, the thing is that that the argument, the base case is really rather easy. You know, n equals 1. 1-dimensional case is very easy. People immediately realize there must be an odd number of switches. This one requires a little bit of ingenuity, right? This idea of walking through doors. Okay? The reason I did the 3-dimension one was to say that to go to 3 dimensions, it doesn't require any more ingenuity. The same argument just works, right? Okay? But if you want to write it down formally, you'll say, yeah, the base case is n equals 1, and then you wouldn't show both the things. This was just to show intuition.
Okay, thank you.
Yeah. Okay, so formally you could skip that. Okay, so what does this have to do with rental harmony? Okay, so you have these. So let's do rental harmony in 2 dimensions. Okay, and let's say you have a blue room and you have my yellow is missing. Okay, and you have a yellow room, right? And you want to split the rent and you want to decide who gets which room, right? So what you can do is you can take a segment, okay, this, and divide it into small pieces, all right? And you can make this as small as you want, arbitrary small. So let's say your total rent is 50,000, right? So you can then put maybe 20,000 of these things. So, so you get a very fine answer. We'll see why that is important. Okay.
Sir, what is the problem that we are dividing what?
Okay, so we are going to pay rents. 2 roommates are going to, they have to decide how much rent each roommate pays and which room does which roommate get. Okay? All right? And so what we do is we take a line segment. All right? So this point is 0 and this point is 1. All right? Now this 0 stands for the percentage of what rent percentage you will pay if you're going to take the blue room. All right, so here, this point represents that the person who gets blue room pays nothing. Okay, and the person who gets the yellow room pays everything. All right, so this is, right? And let's say this is saying that the person who gets blue room pays, let's say, 10% of the rent, and the person who gets yellow room pays 90% of the rent, and so on. And over here, the yellow guy pays 0%. Okay, and the blue guy pays 100% of the rent. Okay, right? So this is what this line represents, and you can make this as fine as you want. You can go to any scale. You can go to rupees or paisas or whatever. Okay. Now what you do is you have two roommates. Let's call them Amal and anyone with a B? Bilal. Okay. All right. Okay. So what you do is you alternatively put A's and B's here. This just happened to be A. Okay. And you ask A, if this is the rent distribution, which room are you going to take? And here you ask B, if this is the rent distribution, which room are you going to take? And then you ask A, if this is the rent distribution, which room are you going to take? All right, so that's the question you're asking them, okay? And you assume that these guys are misers. In the sense, if they get a free room, you know, they love it, okay? So when you assume these guys are misers, here A is going to choose which room? Blue. Okay. And here it doesn't matter whether it's A or B, you know, let's put ... Okay? Whoever it is, what are they going to choose? Yellow. Okay? Okay, so we are all set up for the Sperner setting. And now, this guy chooses a room, you know, or according to whatever rent distribution, and we go and find our monochromatic edge. Okay? And this monochromatic edge tells, so for example, this says B gets room number yellow, A gets the blue room, and the rent distribution you read off from here. Just take the average.
Take the average, okay.
You can take the average, or you can just say take left side or right side because it's within pennies of each
When
other.
you're the same color, there will be conflict.
Yeah. Okay, so for example, initially you'll have blues, right? Because the blue is so cheap.
Yes, exactly.
Over here also, initially you'll have yellows. But at some point, you know, people are going to start saying, wait a minute, blue is too expensive for me now. Okay? Yeah.
That would be point equal.
Huh?
That would be point where the distribution is equal. 0.5.
No. That depends on the preferences. Look, I may like the yellow room because it has a window, and I'm willing to pay 70% of the rent to have a window. I mean, there are people like that. Yeah. Okay?
So then then the first one, 0, 1, there can be person who would be saying, I am not getting the very cheap room, I will buy the room. That A1, there can be a preference that I won't be buying, I am not be living in a room which is totally free.
Yeah, so there's an assumption that if you get a free room, you're going to take it.
And after that, the second one, in which the distribution is 0.1 and 0.9.
Yeah. So now it's B's choice. B gets to choose the room.
It can be anyone.
Yeah, but he has to say that if this is the rent distribution, do I choose yellow or do I choose blue? Okay. All right, and then the next is, blue pays 20%, yellow pays 80%. And you ask A, if this is the rent distribution, which one would you choose? Okay, and you keep doing that, right? Okay, so when you come to multi-color, when you come to a multicolor edge, this is almost an agreement, right? Because ये मैंने 0.1 रखा है यहाँ पे, इस इंटरवल को आप 0.0001 कर दें ना, बहुत छोटा कर दें. So then you have almost agreed on it's almost agreement.
रूम्स की अगर वैल्यू बिल्कुल एक जैसी होगी तो फिर 0.5 0.5 पे
Yeah.
लेकिन अगर एक बहुत अच्छा रूम है, बहुत
Yeah,
बुरा रूम
yeah.
है तो फिर एजेस पे आएगी.
Yeah, and it also has to do with the affordability of people. Okay, so for example, if there's a rich guy, all right, they may actually want to pay a lot more for the room that they only like slightly, right? Because their money is coming from their dad, So it's.
If you are implementing this, say, in a computer as an algorithm, so like there will be.
Yeah.
Okay, so if this is a computer program, so so there will be like say 100 iterations, each asking a person like how much are you going to pay, how much are you going to pay.
Over here, you can do a binary search in one dimension. Okay, so what will happen is I'll go and ask A, which one will you take? And then I'll go and ask B here, which one will you take? And by the fact that they're being misers, these will be different colors. Okay, and then I'll ask the middle rent from, let's say, A.
Okay.
Okay, and if they say blue, then this side is still fine, otherwise that side is still fine. So you can go logarithmic on this in one dimension.
Sir, what if we have multiple cases of alternating colors? Then there will be agreements on more than one kind of
Yes,
rent. Then
okay,
what?
yeah,
That-
that's
Not a mathematical problem, but still.
Yeah, that's a very good question. What if there are multiple solutions? Which one do you choose? Okay, in one dimensions, I can give you a reasonable answer, but in two dimensions and three, I don't have a good one. Right? In one dimensions, what I would want to do is I would want to take the biggest edge, where there is a switch of colors and agreement. Okay, and then take the average of that.
What do you mean biggest edge? Or aren't these all this? So these can be different lengths.
No, so
These can
look,
be-
so if there is more than one switching edge, then what I would do is I would try to find a yellow and a blue, okay, where there is, this is labeled by A and this is labeled by B, and then take the average of that. That's what I would probably do.
But if they are far apart, then their preferences are very different from each other. Shouldn't they be very close?
Look, in one dimension, okay, what is going to happen is it's going to go blue, 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 all right, and then it's going to go yellow, 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 right? That would be the logical thing for it to happen. But what might happen, it may go blue, 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 and then it may go, B may switch because they are poor, right? And they say, I can't afford this room anymore. But A may still stick with it and say, no, I still want this, I still want this, I still want this. So in that case, you would try to see how much more is the other person willing to pay for the room that is not being given to you, and so somehow give that benefit to you. Yeah. This is how I would resolve it. I don't, but otherwise.
Not really a mathematical problem.
Yeah.
This is just a.
Yeah. Okay. Yeah. So now how do we do rental harmony when you have three roommates? Okay. All right. And the thing is that what you realize is that a triangle actually models a distribution of rent in three partners. Okay, and the way you can see that is typically we draw triangles in 2 dimensions, but let's draw it in 3 dimensions. Okay, so this is your x-axis, this is your y-axis, this is your z-axis. So this point is, I guess, 1, 0, 0. All right, and this point is 0, 1, 0, and this point is 0, 0, 1. Okay, and think of this triangle that's made by connecting these three vertices. Okay, right? Each point here, okay, let's say x1, x2, x3, what is the property it has? Its property is that x1 plus x2 plus x3 is exactly 1. Okay, and xi's are okay, right? So these
Probabilities.
yeah. So it's like probabilities, right? So it's modeling. So you have a 3 outcome event. A possible outcomes are 3, and you're distributing things like that. That's like a renter thing. Another way to think about this is, and this is an exercise I'm going to give you. If you take an equilateral triangle and pick any point on it, right? And now you find the distance of this point to this edge, to that edge, and to this edge. Let's call this A, B, C. Yeah, okay. And there's a theorem called Vivani's theorem, which says that A plus B plus C is actually a constant, independent of where you are. Okay? All right, and so by normalizing with the constant, it also gives you a way of getting probabilities. Yeah, yeah, and it's a really a cute theorem. You can go home and try to prove it. This has to be equilateral. Yeah. वैसे नहीं होगा. Yeah. This is for equilateral.
Triangle with the same vertices.
ना किसी भी कोई इस तरह का टेढ़ा मेढ़ा होगा ना तो एज पे ले जाओ उसका जो एल्टीट्यूड होगा
वो डिफरेंट होगा मगर किसी टाइम पर भी ना किसी भी पॉइंट के ऊपर आप 3 एल्टीट्यूड लेंगे तो उनका सम कांस्टेंट होगा वो एक ही होगा उस ट्रायंगल का.
I think he is right. If let me just sort of digest your, because I'm just thinking about Vivani's proof. क्या होता है इसका proof ये होता है कि you make 3 triangles. Okay, one is this yellow, the other one is blue, and the other one is red. Okay, and now you say the area of the blue triangle is base times altitude, and this is base times altitude, this is base times altitude. The base is constant. Okay, all right. So the sum of them is the total area, and so the sum of the altitudes.
Only for equilateral triangles.
Yeah. So
सेंस नहीं बनती ना अगर दूसरा कोई ट्रायंगल है तो फिर it has to work for all the points of the triangle. Vertices पे काम नहीं करेगा.
Vertices पे काम नहीं कर रहा.
तो फिर किस तरह वो हो ही नहीं सकता. फिर अगर vertices पे काम नहीं कर रहा तो उस पे work नहीं करेगा.
Yeah. So what he's saying is if you have a let's say isosceles triangle, when you're here, the total is very tall, but when you're here, the total is not too much. Yeah. And now what you can do is you can try to see why Vivani's argument doesn't work here. And you will learn something. Yeah. So where is the critical? Oh, I think I found out why it doesn't work. Okay. But you have to do it. वो हमने यहाँ पे argue किया the bases are the same. And that argument here doesn't translate. Right? So that's okay. So what you do now is so any point in this triangle is a way to divide the rent 3-way. Okay, all right. And now what you do is you play the Sperner game again. You make okay, and I'm not going to make, you triangulate this, Okay. And now you have 3 roommates, right? Emil, Bilal, and who else? C for Sajad, huh? Okay. Because we are become हम modern हो गए हम जानबूझ के चीजें misspell करते हैं, right? So you do this, and you know, here is your picture of your apartment, okay, which has a blue room, it has a red room, and it has a yellow room. Okay, and now what you do is you label this thing, and here there is a little bit of hand waving that I'll do in this way: A, B, C, A, C, B, and this is going to be C, this is going to be B, I guess this has to be A, and this is going to be A.
Shouldn't there be only 2 people on one edge, like over there?
नहीं, अभी हमने कलर्स नहीं किए.
Same argument apply करने के.
हाँ, अभी हमने कलर नहीं किए.
इसकी जरूरत नहीं पड़ेगी.
ABC are not colors. ABC are names of people. Okay. What I do is, I go to a point here, okay, and what is it labeled? A. All right. So I ask him, in this rent distribution, which room will you choose? Okay. So this doesn't tell us the color. It just tells us which roommate are we going to inquire. Remember उसमें जब हमने one dimension में किया था, तो हमने उसको A B लेबल किया था. एक बार हम एक रूममेट से पूछते थे, दूसरी बार हम.
इसकी भी सेंस बनती है ना. हैंड वेविंग आप क्यों कह रहे थे? क्योंकि हम ऑल्टरनेट कर रहे हैं ना, A B C, फिर all triangles must be such that they have A B C on each corner. आपने यही algorithm लगाया ना.
हाँ, उसमें I have to actually prove to you that such a labeling is always possible, in which every little triangle has ABC, 3 labels. Every triangle. Okay? But I have to show that there exists one. Okay? Obviously, for all to ho nahi sakta, you can just mess it up, right? There exists one. So I have to do that, right? Okay. But, and over here, this is labeled B. So what I do is I tell him the rent distribution to B and ask him, which room would you like? Okay, all right. And so what would a little multicolored triangle achieve? Harmony, right? Harmony. The 3 have agreed, or almost agreed. Up to pennies, you know, they are agreeing on.
Centroid.
Yeah.
Average.
Yeah.
You can't apply binary search in it, right?
Oh, no, I thought about it for a day or so, and it seems hopeless to me. Actually,
So many points.
it seems hope. अच्छा, लेकिन यहाँ पे अभी हमने जो है वो हमने जो है, so what is this point? This point is 1 0 0. Okay, this point is 0 1 0. This point is 0 0 1. Okay, and let's say this is the yellow room, third one. Second one is the red room, and the first one is the blue room. Okay, all right. Now we know that these guys are misers. Okay, so on this side, okay, the last room is free.
Last room is
free. यहाँ पे भी 0 है, यहाँ पे भी 0 है, इनकी कोई भी weighted average ले लें, तो last room is free, which means there will only be yellows here. ठीक है ना? Okay. All right. अच्छा, यहाँ पे कौन सा room free है? First room is free. So there will be only blues here. Okay? Okay. All right. And on this side, which room is free? the middle room is free, right? So they will all be red. Okay. All right. So it seems like it's working, right? It's like a Sperner kind of a thing. But what color will this vertex get?
Can be either red or yellow,
It
because
will be
both
either-
are free. Both
Yeah,
are
both
free.
are free, right? And similarly, this vertex can get
Either red or blue.
red or blue.
Red or
Okay,
blue.
and this will get either yellow or blue. And it's not necessary that you get three distinct vertices of
Okay,
three
then
different
same
colors.
argument, we can build something like this.
Yes. Okay, so what you do is, this is the beauty of understanding proofs, is you don't apply Sperner's lemma directly, you mimic the proof. Okay, so if they happen to be all three different colors, you know, you're Sperner and you're fine. So let's try to not do that and see what happens. Okay, so for example, I say, okay, on here, red appears, okay, and over here also, red appears, right? Red is allowed there. Okay, now we go and examine this vertex, right? What are the colors? Red वहाँ पे, have I done this correctly? Red, red, okay. And on this, red, yeah, the middle room is free. और यहाँ पे कौन से आ सकते हैं?
Yellow or blue.
Yeah, yellow or blue आ सकते हैं. All right, so let's say if this is yellow. All right, then if you see, this side has exactly one switch. All right, so we do the Sperner lemma with yellow and red. Okay, they can't escape from here, the whole argument goes through. Right, there's only one way to enter. The second possibility is that this vertex is actually blue. Okay. All right, and okay, in this case, the bottom edge is Sperner. It has exactly one switch, and you can repeat the argument. Okay, so it's a Sperner.
Okay, this is.
Yeah, thoda sa, you have to tinker it a little bit. You have to do a more general statement in which saying that you can't escape from two sides, and the third side has an odd number of door or one door.
ये तो बहुत
Then the
आसान है,
Sperner.
सिर्फ एक
Yeah.
door है, तो obviously you will get stuck inside.
Yeah. So yeah. Okay, so you achieve rental harmony this way. Okay, all right. So now I want to do one more thing, and I'm going to leave one thing for you, which is cake cutting. Okay, if three people want to divide up a cake, right, then you can have percentages. You can say this is my cake, this is x1, okay, and then this is x2, and this is x3, all right, and you want to divide it NV free. Okay, so what you can do is then every point here is just a way of cutting up the cake. And then you ask different people which piece they will take, and you can solve the cake cutting problem. Now, I want to do one more thing, which is really fun, and that's called the Brouwer Fixed point theorem. BRO W.
Can I just ask a question about the...
Yeah.
So you intentionally made two sides all monochromatic intentionally so that you have a single switch on the bottom side. Am I correct?
No.
That was your, like
No.
that you designed it that way.
नहीं, that is not the case. देखो, ये जो vertex है, ये कहती है कि पहले रूम वाला 100% पे करेगा और बाकी दोनों फ्री हैं, राइट? ये कहती है कि दूसरे रूम वाला 100% पे करेगा, बाकी दोनों फ्री हैं. What about all the points here, they will be of the form PQ0. Okay, because remember, the points on this line are convex combination of these two. So, unka aakhri component 0 hoga. But we are assuming they are misers. Okay, so they will keep choosing the last room. Okay, so all these would be yellow. Okay, that is consequences of the miserness condition.
Yeah, I'm talking about the edge nodes. So like your intention. Okay, I'm talking about like say the top node. So you could have chosen two colors over here.
हाँ अच्छा यहाँ पे so there will be only yellow, यहाँ पे there will be only red और यहाँ पे there will be only blue. Okay? इसके बारे में हम क्या कह सकते हैं इस वर्टेक्स में? इसमें दो रूम्स फ्री हैं.
So I can put
Either yellow or red.
दोनों possibilities रख के उन्होंने
ठीक है ना? So here also I can put red and blue. Here also I can put
yellow and
blue. So इसके 8 cases बनेंगे.
ठीक है.
ठीक है ना? आप उन 8 cases को one by one analyze कर सकते हैं और उसमें you can figure out के Sperner condition is satisfied. Okay? But we did it this way कि अगर ये तीनों different colors के हैं तो पहले हम कर चुके हैं ये problem. Okay? So इसमें से कोई भी दो same ले लो तो बाकी जो दो उसकी possibilities थी we argued those. So that was like a clever way of cutting 8 cases go into fewer one. Yeah, so you can, I went through all 8 cases, the first time I did it. Yeah. Actually, it's really strange that first time when you do things, you should do it in detail because, right? But in a talk, you can't do that because then it just takes too much time. So, yeah, okay. All right, so what's the Brouwer fixed point theorem? Okay, so by the way, if there's any physicist, forget your physics. I'm talking about mathematics. Okay, so let's take this. I have a notepad and I pulled out this piece of paper, and let me crumple it. Right? Really crumple it. Okay, let's crumple it. Okay, so it's pretty crumpled. So all right, now let me put it back on here. Now, Brouwer says that there is one point on that paper which is lying exactly on top of where it was before. Okay, that's the Brouwer fixed point theorem. Okay, as long as you didn't tear up the paper. Okay, so let's write it down. If you take a function which is from a rectangle to a rectangle. Actually, you can do it from a triangle to a triangle also. Fill triangle, okay? And f is continuous. As long as it's continuous, it has a fixed point. Okay? All right? Another way of thinking about this is, think of a city of Islamabad. Okay, and let me go and buy a map. Okay, and let me go to a very weird place like the black hole.
The black hole is a weird thing?
You're here to listen to my lecture now. How weird is that? Okay. Yeah, of course it is weird.
We are cutting cakes using mathematics. We are this weird. Instead of using knives, we are proving how to cut a cake.
How to cut a cake, yes.
We are so weird we are.
So it has, so every, it has, so you buy this map of Islamabad, and anywhere you go on the map, there will be a you are here point. There will be a point on the map which is exactly on top of where it says it is. Okay? And that you are here point will be there even if you crumple up the map and put it in your pocket. Okay, there'll always be a point on the map which will be on top of where it says it is. Okay, right? So that's the Brouwer fixed point theorem. The only way.
Can we prove this in the way that, for example, for a one-dimensional function x and y, So if you have any continuous curve between 2 points, like any old shape, so it will always intersect with the y is equal to x line.
Yeah,
At least 1 point. So
Yeah.
that is kind of a proof for Brouwer's fixed, that 1 point will always remain in its original place.
Yeah, so in one dimension, Brouwer fixed point theorem is like the intermediate value theorem.
Exactly, that's it.
Okay, so take a function from -1 to 1, all right, and it's continuous. So let me draw it here. Okay, so here's -1, and let's say this is +1. Okay, and here is your identity function. And what you're saying is that if you take any function, its graph must cross this graph. And the idea is, well, if f of -1 is -1, you're done. Okay, and if f of +1 is +1, you're done. So the only case you have to assume is when this is above this function here and it is below this function here. Okay, and so it must cross. And formally what you do is you take the difference of those two. And you realize that this function is negative. The difference of that function is negative at -1, positive at +1. So by the intermediate value theorem, it must be 0, which means the two things cross. Okay, so that's the fixed point theorem. But here it's saying something really beautiful. Okay, and this works in any dimension. All right, so for example, if you had a mathematical tea, all right, and so you take a cup of mathematical tea and you gently stir it, right? There'll always be a molecule, a mathematical molecule, not a physical one, which hasn't moved. Okay? I mean, that's bizarre. At any point, okay?
Say pivot. Just like in physics, pivot point, about pivot point.
Yeah, I don't know much physics. I don't know any physics. Yeah, but look, here you're talking about any continuous function. It's not a rotation. I mean, continuous functions can be really, really bizarre, right? You know, they can, they may not even be differentiable at all. Okay, so these functions don't have to be differentiable. In fact, you can construct continuous functions which are nowhere differentiable. Okay, even those kind of bizarre animals will have a fixed point.
Fractals होते हैं ना जो nowhere differentiable होते हैं.
Yeah.
Fractals basically.
Yeah, as long as the domain and the range are the same.
Yes.
And what is important about this domain and the range is that they have to be what we call compact. And compact means closed and bounded. Okay, bounded, it can't be an unbounded set. Because in unbounded sets, you know, you can just continuously remain above the x, you know, whatever you want, okay? And if it doesn't contain the boundary, then you can do strange things also. You know, you can let the function go to infinity and be very bizarre. So these things have to be what we call compact. Okay, so let's prove the Sperner Lemma, okay? Let's prove the Brouwer fixed point theorem via the Sperner Lemma. Okay, all right. And I'll have to do a little bit of hand waving here. Okay, so here's our triangle, and we'll prove it for triangles because, I mean, the shape is just coming out of here. So we have a function from this triangle to itself. Okay, and imagine these pictures look the same, right? Okay, so which is a continuous function. It's mapping these points to these points, all right? So here you will have a point P1, P2, P3, okay? And it will be mapped to something which will be f of, you know, that, which will be Q1, Q2, Q3, right? Okay? And let's assume that this function has no fixed point. Okay, so then P1, P2, P3 is not going to be identically equal to Q1, Q2, Q3. So what I can do is I can look at this difference. Okay, all right, and this difference is not going to be 0. Okay, because Q is, otherwise that is a fixed one, that's what I'm looking for. Okay, so this is not 0. Now my claim is that in this vector, if it's not identically 0, you must see a positive number and you must see a negative number. Okay, and remember that P1 plus P2 plus P3 क्या थे? ये 1 थे, and Q1 plus Q2 plus Q3 क्या है? ये भी 1 है. ठीक है ना? अब देखें, अगर इसमें सिर्फ पॉजिटिव नंबर्स आ रहे हैं, that's telling you that Q1 is greater than P1, Q2 is greater than or equal to P2, and Q3 is greater than or equal to P3, which tells you that the sum of Q's is strictly greater than the sum of P's, which is a contradiction. Right? Okay? I mean, just think about it. If there's 100%, right, and you divided it into 3 parts, and then you divide it again into 3 parts, अगर आपने इधर एक छोटा पार्ट लिया है, तो आपको एक बड़ा लेना पड़ेगा compensate करने के लिए. Right? Okay, so both signs must appear, and in particular, a positive sign will appear. Okay? All right. Okay. So, okay. All right, now what we do is, so what we can do is we can look at the maximum of this quantity. Okay? All right? Okay, we can look at the maximum this quantity. This is a continuous function, right? Because Q's were a continuous function, max is a continuous function, this is a continuous function, and this maximum is never 0.
Always positive.
It's always positive. It's always positive. Okay, now if the set is compact, it turns out that every function on a compact set must attain its minimum and maximum. Okay, that's where you need the compactness. All right? Okay, so this minimum is attained.
What
Minimum of this function is attained. All right? So that means that I can say that max of Q1 minus P1, Q2 minus P2, Q3 minus P3 is actually greater than some positive quantity epsilon. Right? वो मतलब, okay? Right? It's greater than some positive quantity epsilon because its minimum is attained. You know, let's call that minimum epsilon. That can't be 0. So it must be some, okay, for some positive epsilon. अच्छा. अब मैं क्या करता हूं कि I create a very fine grid here. I triangulate this. Okay? All right? And I make this grid so fine so that when I move on the grid, the function can't change by more than epsilon over 10 or something like that. Okay? And for a continuous function, you can do that. Right? You know, that's the definition of a continuous function is, you know, for every epsilon, you can find a delta. And it turns out that on a compact set, if a function is continuous, it is what is called uniformly continuous. So the delta actually doesn't depend on the location. It's a global thing for the entire thing. All right? So now I make this very, very tight grid. Okay? And now I go to this point, right? और यहाँ पे जाके मैं इस फंक्शन को देखता हूँ, right? ये कहीं ना कहीं एप्सिलॉन से एक्सीड करेगा, right? अगर ये पहले कोऑर्डिनेट में एप्सिलॉन से एक्सीड करेगा तो I'll put a red here. अगर वो दूसरे कोऑर्डिनेट में करेगा तो I'll put a yellow. अगर वो तीसरे कोऑर्डिनेट में करेगा तो I'll put a blue. Okay? All right? और अगर दो में करे तो फिर मैं पहला वाला ले लूंगा. ओके?
एप्सिलॉन कुछ तो हो सकता है. It may be equal to epsilon, maybe the minimum point.
हाँ.
वो भी तो हो सकता है.
I'll go and search for something which is greater than or equal to epsilon. तो वो 3 कोऑर्डिनेट्स हैं. एक ना एक तो मुझे मिलेगा ना. तो मैं उसका इस कोऑर्डिनेट को मैं रेड कह रहा हूँ, इसको ब्लू कह रहा हूँ, इसको येलो कह रहा हूँ. I just record that coordinate here as a color. Okay? All right. Now, remember what this point is. This is 1, 0, 0. इसमें से जब मैं कोई भी q subtract करूंगा, only the first coordinate can be, because remember these two are 0. Okay? So q's will be larger than this. So this will always be colored red. Okay? Similarly, you can argue this will be colored yellow and that will be colored blue. And you can argue that यहाँ पे red नहीं आएगा. Alright? So you get this Sperner setting.
फिर से सर ये रिपीट करना, फिर से सबसे ऊपर वाला किस तरह रेड होगा?
Okay.
सबसे ऊपर वाला जो है वो मतलब उसमें एप्सिलॉन से बड़ी वैल्यू आएगी ना. फर्स्ट पोजीशन.
Okay, sorry मैंने इसको उल्टा लिखा है. Just make this P1 minus Q1. ठीक है? अच्छा, ये पॉइंट क्या है? 1, 0, 0 है. इसमें से आप कोई भी Q सब्ट्रैक्ट करेंगे तो पॉजिटिव कहाँ पे आ सकता है? फर्स्ट पे आएगा. सो दिस हैज टू बी कलर्ड रेड. ये पॉइंट जो है 0, 1, 0 है. इसमें से कोई भी Q सब्ट्रैक्ट करें, सेकंड पे ही आएगा. सो दिस हैज टू बी देन whatever the second color is, let's say yellow. And you know, the third color, blue here. Okay? अच्छा, और ये क्या है? Actually ये point 0, 0, 1 है. Right? और इस edge पे the first coordinate is 0. So it can never be colored. It's the same.
So you will exactly. So there will be a point 0, 0, 0 in the middle somewhere. 0, 0, 0 where that will be the fixed point.
हाँ, नहीं, हाँ, वो हम देखते हैं कि so you find a little triangle, okay, which has all 3 colors. Let's say yellow, okay, let's say blue, and red. Okay, all right. Okay, so this one had a positive here, positive epsilon here. All right. Okay.
Second येलो वाला सेकंड पे नहीं था. येलो वाला के सेकंड कोऑर्डिनेट था.
Okay. All right. So this has a positive epsilon here. Okay. This has last one. This has a positive epsilon here. Okay. And this has a positive epsilon here. Okay. अच्छा, अब अगर इसमें यहाँ पे positive epsilon है, तो one of the places must have a negative. Okay, so you tell me which one. This one or that one? If you tell me this one, then I'll say this is a negative. Move to that point, you went from a negative quantity to plus epsilon. That's not continuous. Remember, we chose delta that the function can't change that much at that scale. All right? So if you tell me this is a negative, I move here and I get a contradiction. If you tell me this is a negative, I move here and I get a contradiction. Okay, so the function is not continuous.
So that's why all coordinates must be 0.
Yeah, well,
Here.
yeah, that's the, yeah. So you conclude that we
All
started by a counterexample, so the counterexample doesn't exist.
Doesn't exist. Okay.
Yeah, yeah. Yeah.
So So this is the contradiction we reached.
Yeah.
So
Yeah.
And the starting assumption was what was the initial?
The starting assumption was there was a function which had no fixed point.
Oh yes.
So there's no a function which has no fixed point. What we did was we took the point from it, we subtracted the function value coordinate by coordinate, all right, and we said that can never be 0. Then we observe that it can, if it's never 0, it must have positive and negative both quantities in it, all right, and then we said, okay, we'll pick up the maximum positive quantity, and that never reaches 0, okay, and so the function must attain its minimum, so it must be above some threshold epsilon all the time. Then we said, okay, given this epsilon, we make a grid which is tight enough so that when you walk on a little piece of the grid, you can't change more than epsilon. Yeah, you can say epsilon over 100 or something, just to be safe, okay. So we said that, okay, and we found that delta, we put out that grid, and then we colored these things, all right, accordingly, looking at that. And then we said, okay, but Sperner says there'll be a multicolored triangle. Okay, let's say it's this. Now, here's a positive epsilon. One of them has to be negative. If this is negative, I move there, I get a contradiction. If it's negative here, I move here, and I get a contradiction. Okay, it's really beautiful.
Also, can we locate the exact, is there a way of locating where the fixed point exists for a particular mapping?
Okay, yeah. So, are you familiar with NP completeness?
Yes, a little bit.
Yeah, so there is, so in computer science, when you have a computational problem, right, we cannot usually prove that they are provably difficult. Okay, so we have this notion of what we make is something which is called a complexity class. Okay, and then so here's a class of problems, thousands of problems which are in this class, and we say this problem is complete for this class. In the sense that if you solve one NP complete problem, you'll solve all of them. Okay, so that gives us evidence that the problem is hard. We haven't been able to prove yet, right? So जब आप एक NP complete problem पे काम कर रहे होते हैं, तो आप सारों पे कर रहे होते हैं. Okay, so that's why we think that these problems don't have a polynomial time algorithm. All right. Okay, so there's this class called NP complete. So for example, if you're working on the traveling salesman problem, you're also working on the scheduling problem. You're also working on satisfiability. You're also working on graph coloring. These are all equivalent problems.
Same for this one, bro.
No. So the thing is here, NP completeness is about decision problem where the answers are yes and no. In these problems, the answer is always yes. If I give you a function and say, it's continuous, and ask you, does it have a fixed point? You don't even have to look at the function. You can just keep saying yes, right? If I give you a Sperner coloring, right, you can just check the edges of it and see it's Sperner. You don't even have to go inside and you say, oh, yes, it has a multicolor. So these problems are different where you're not really saying, does it have a property? You're saying, find me a point with that property. Okay, so these classes cannot be captured by NP completeness. So for these kind of classes, there is another class that is being defined, which is called PPAD, right? Which stands for polynomial parity argument for directed graphs. Okay, and computing Nash equilibria, computing fixed points is complete for this class. Okay, all right, so
this PPAD is part of NP.
No, because NP complete problems are decision problems.
No, the finding the specific fixed point, that problem. So that is okay. So PPAD is different from NP.
Yeah, it's a different class of problems, right? So for example, NP completeness doesn't really capture counting questions. So for example, you can say, here is a graph, okay, does it have a 3 coloring? Can I color it with 3 colors with edges getting different colors? But you can also ask the question, how many ways can I color it with 3 colors?
Yes.
That becomes a different question. So for that, there's a different class which is called Sharp P. Yeah, yeah. So, but in the same spirit, you know.
So I have a question, like it's about counting. So when we are talking about NP class, so there is clique problem.
Yeah.
How many friends? So to me it seems more like related with numbers, or the knapsack problem where we are talking about how many, what is the maximum cost you can put in the bag. So to me it seems more like related to numbers.
No, no, yes, you are right. Yes and no is okay. So, okay. So, for example, the clique problem. Okay, the way it is placed in NP is the input is a graph. Okay, and a k. Okay, and the question is, does this graph have a clique of size at least k?
Okay.
So you convert that problem into a yes/no question. And now this decision problem is NP complete.
Right.
Okay? All right? So but NP is always a decision problem. Okay? The problem is with these problems, you can't convert them like that into yes/no questions.
Okay.
You can say, does it have a fixed point in this region? But that doesn't really help you that much, even if you get an answer to that. So the parity argument for a directed graph goes as follows. It says, suppose if I have a directed graph with arrows, direction in the arrows, and there's a vertex whose in degree is not equal to the out degree, then there must be another vertex with that property. Okay?
The property of the in vertex.
Yeah, so if I have a vertex V, such that in degree of V is not equal to out degree of V, okay, then there must be a W which is not equal to V having the same property. And the reason for that is because the sum of the in degrees is equal to the sum of the out degrees. So if you have an imbalance somewhere, it must be compensated somewhere else. Okay. Shall we call it a day?
Yes.
Yeah, great.
Any further questions? Very chalk.
Okay. Just a question. So, we can't convert this problem that we discussed into a decision problem simply because there are infinitely many points because of the compactness property. If there are finitely many points, then I think this will not.
No. I'll tell you what the input to this problem is. So what the input to this problem that typically is given by. What you do is you take a function. You don't have a function. What you have is you have a grid, right? And you can only ask the function value at a grid point. Okay, so let's not do the triangles. Let's say we do a square. So what happens is I have given you a mesh, right? And I say, here's my function, all right? And I'm going to only tell you the function value f at these points, and you can ask me those function values. For each one of them you ask me, I charge you $1, right? What about at here? What's the function value? It's linearly interpolated. You and I agree that. Okay? All right? So that's how they model the problem. Okay. Okay. Thank you. मेरा डब्बा मुझे मिल गया.
ये मैं देख रहा था यहाँ पे. हाँ,